Hi, everyone, and welcome back. It's Kira Garfolo with Greenville Tech's MAT-109. Today, we're going to start section 6.1, which covers the higher degree polynomial function. So remember from a previous chapter that a polynomial is an algebraic expression that contains a finite number of additions, subtractions, and multiplications of constant and non-negative integer powers of variables. So that's really math speak, but you're just saying that you have some number times x cubed plus some number times x squared plus some number times x plus a constant. Or we don't have to start with x cubed. We can have x squared as our top one, or we can have x to the 17th as our top one. We have these various powers of x that go throughout, and we're adding and subtracting different coefficient values. Now, the degree of a polynomial is simply the highest power of x. So when I talked about cubics there, where I talked about x cubed, then 3 is the highest power of x, so the degree is 3. If I have x to the 5th plus blah, 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 then our degree would be 5, because x to the 5th is the highest. Something to keep in mind here is it's not necessarily the first term. They don't necessarily have to be written in order. So if you had 5x plus 3x cubed, then 3 is still the degree, because x cubed is the highest value of x that we have. So a higher degree polynomial function is simply just a polynomial function that has a degree higher than 2. So far we've talked about that degree of 1, where we have a linear term, I suppose. We have the quadratic function, where we had a term that was x squared. And today we're going to talk about things that are higher than x squared. So in general, we can write it in descending order. So it's ax to the n plus bx to the n minus 1 plus all the way down to our constant term. So this could be, 3x to the 5th plus 2x to the 4th plus something x to the 3rd and somewhat all the way down. There's some special cases of higher degree polynomials. Like I said, you could have x to the 121st power and have a degree of 121, and that would be fine. But we're going to talk about some special cases here that are going to stick with us for the rest of this unit. Cubic functions have a degree of 3. So we can write them in the general form here of a times x to the 3 plus b times x to the 2 plus c times x plus d. So a here cannot equal 0, because otherwise we wouldn't have a cubic term. The rest of them can be 0, but a cannot. We have to have a valid x cubed term. So remember that something to the 3rd power is cubed, hence the name cubic. Quartic functions are another special case. And in quartic functions, we have x to the 4th. So remember 4, quart, that's where that comes from. And it's just like cubic. We have a times x to the 4th plus something times x cubed all the way down to a constant term. And again, a cannot be 0, because otherwise we wouldn't have an x to the 4th term, so it wouldn't actually be quartic. Now let's talk about the general graphs of cubics and quartics. So cubics, remember that's x to the 3rd, has at most 2 turning points. So a turning point is where it goes from increasing to decreasing, or decreasing to increasing. So here, in cubics, we either have 0 turning points, like in this example right here. It has little corners, but they're not actually turning points, because see, this is always going up. It never turns and goes back down. It slows its increase, but it continues to go up. So this is always increasing, and this one is always decreasing. It goes down and it slows itself down, and then it speeds back up, but it doesn't actually change direction. It's always decreasing. Over here, we have 2 turning points. So we're going to go up, 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 up. We're going to go down the hill, and then we're going to go up again. So you can think of these little roller coaster humps, right? Where it actually turns and goes from going up to going down. It's considered a turning point. Here we're going down. We have a turning point because we're going up. Another turning point because we're going to start going down. So cubics can either have 0 in the case that they're always increasing or always decreasing, or they can have these 2 humps. Okay, these 2 turning points. Quartics, on the other hand, have at most 3 turning points. So they can have 1 or they can have 3. Those are our options here. So here we have kind of a parabola where we go down, 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 down. We hit a turning point and turn around and go up, and that's all that goes on. you can have the same reflected thing where you're going up, 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 hit a turning point, and go down, down, down. This one isn't such a pretty parabola, and you can see here that we only have one turning point again, though, because it goes down and it slows down, but it doesn't actually go back up. And it speeds back up, but right around here, it's going to pick up and turn around and go up. And then we have these W and M shapes that are our cortex, and they have 3 turning points, because here we're going down, we hit a turning point, we turn to go up, hit a turning point, turn to go down, and hit a turning point and turn to go up. And the same in this reflected case of M. For a turning point, it has to actually turn and go the other way, not just slow down or speed up. So again, a turning point is where that graph changes from increasing to decreasing or vice versa. In math speak, we don't typically call them turning points. We call them local extrema, okay? Because they're local extreme values. It's as high as it goes in that area, or it's as low as it goes in that area. A relative or local minimum is one type of local extrema, and it is where a function changes from decreasing to increasing. So think about that. You've been going down, 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 down. You hit, and you turn and go up, so that's as low as you're going to go in that area. So it's a local minimum. On the other hand, a relative or local maximum is where it changes from increasing to decreasing. It's as high as it goes before it stops and turns and goes the other way. You can actually use your TI calculators to find these coordinates, just like you use in the calc options where you're finding zeros or anything else. You can use that calc, and it has minimum and it has maximum. And you'll just have to tell it which area you want, and it'll spit the coordinates out for you. So again, graph the function and go to calc, and you'll have to zoom in on it kind of similar to the zero feature. It'll ask you a lower bound and an upper bound. So let's look here. Let's just look at the graph and let's state the x-intercept, and let's state the coordinates of any local extrema. So we want to know if the extrema is a minimum or if it's a maximum. So first, let's talk about the intercepts of graph A. We see that it touches the x-intercept or the x-axis here at 0, 0. So it doesn't actually cross it, but it touches it. So we have an intercept at 0, and we have an intercept at x equals 3 over here. And it's going to cross there. So if we want to talk about the local extrema, we can trace around. We're going down, 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 down. We stop here and we turn around and go back up. So at 0, 0, we have a local extrema. And actually, it is going to be specifically a local min, because we're going down, down, down. That's as low as we go before we stop and we turn around and we go back up. Then we go back up, back up. We have another turning point or extremum here, and we see that it's at roughly 2, 8 for our coordinates. And that's going to be a local maximum because it's as high as we go before we stop and we turn and go the other way. So here are our answers. Now take a minute and try B for yourself. Again, remember, you can pause, take a moment, and then resume. So first, when we're talking about the x-intercept, we see the graph only crosses or touches once at x equals -1. And then if we look for turning points, it's going up, 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 up. It slows down here, but it never actually turns and goes back down. So we don't actually have any actual extrema here because it doesn't actually change directions. It just changes speed. This is constantly increasing, just slowing down. Now, I like to make a note here about absolute extrema, because the highest point on a graph over any interval is called the absolute maximum, and the lowest point is called an absolute minimum. So a relative minimum or a relative maximum can be an absolute also, but sometimes it's not. Let's look at an example. So if I have this graph, and I'm going from this point to this point, okay, then I see that I have a turning point right here at -0.408 0.272, okay? So this is actually a relative max because it's a turning point where I go from up to going back down. This is a relative minimum here because I'm going all the way down and then I'm turning back up. To determine our absolutes, we need to see the highest y value we get on this interval. So our highest y value is right here. That's as tall as we get, right? So 1, 1 is our absolute max. Now, our absolute minimum is the lowest y value we get. It's not here at our starting point because we can see it goes even lower than that. In fact, our absolute minimum is our relative minimum because that's as low as we see here on this interval. So just keep in mind the differences between absolute and relative, and remember that they could be the same, but they don't have to be. Now, one other feature of graphs of polynomials is called end behavior. And the end behavior of a graph is what happens on the far left and the far right. So as it goes way towards the left towards negative infinity, or as it goes way towards the right towards positive infinity on the x-axis, what is happening to the graph? Is it going up? Is it going down? What's going on? So does it go up or rise as x goes to negative infinity, or does it go up and rise or fall as it goes to positive infinity? So it can either be going up or it can be going down. Let's look at our earlier examples here. So here we see this graph. And if we look and we say, okay, well, as we look towards the left, so as we're looking this way, okay, we're looking towards negative infinity, are we going to need to draw up or are we going to need to draw down to mark that graph? Well, looking to the left, that graph is going off towards up, right? So it's rising to the left. And as we trace it towards the right, we're going to be going down as we go to the right. So this one is rising to the left and falling to the right. These arrows can help. I still draw them too. Let's look here. Take a minute and see if you can get it. If we take our pencil and trace towards the left, we're going to see we're going down. And if we trace towards the right, we're going to be going up. So here, we're going to have it falling to the left, and then it's rising to the right. Looking at a graph like these, it's pretty easy to identify that end behavior. Just trace it with your pencil, right? But what if we don't have a graph? And maybe we don't have our graphing calculator in front of us, so we can't even use that. We can actually use the leading coefficient to tell us about our end behavior. So remember here that the leading coefficient of a polynomial is just the coefficient on that biggest power of x. Remember, it's not necessarily the first coefficient you see. If it's not written in descending order, it won't be. Look for the highest degree of x, and it's the coefficient tagged onto that. As long as we have a polynomial with a degree higher than 0, then we know that our graph eventually goes up or it eventually goes down forever and ever, okay? Remember, if the degree is 0, it's constant, so it's just that flat horizontal line. That's why this doesn't work. But for any of linear and higher, we have this test that'll show us how it works. So if our degree n is odd, and we look at the leading coefficient, so you need to look at the degree of the highest power, and you need to look at the sign on the leading coefficient. So if we have a positive leading coefficient with an odd degree, then it is going to fall to the left and rise to the right. If you have an odd power and your leading coefficient is negative, then it's going to do the opposite. It's going to rise to the left and fall to the right. So notice here, if n is odd, then one side is doing one thing and the other side is doing the other thing. You just need to decide which way they're going. On the other hand, if n is even and your leading coefficient is positive, it rises to the left and it rises to the right. And if that leading coefficient is negative, it's going to fall to the left and fall to the right. So you need to look here and think, if n is even, they're going to go in the same direction as they go off forever. Think about a parabola. Think about x squared here, right? X squared is going to look like that regular old U-shaped parabola, so it's going to rise to the left and rise to the right. I tend to think of x cubed for my odd example, but I guess you could think of just a linear term, right? If it's positive, it's just going to be going straight up like that. So towards the left, it's going to be falling. Towards the right, it's going to be rising. But x cubed works with that too. Remember, if you have your graphing calculator, you can usually work these out also if you couldn't remember the rule. But the rule is really helpful and it saves us a lot of time. I like to keep this organized in a table like this. I think that it just helps. I'm a visual person, so it helps me. But you can kind of memorize this if that helps. And also remember, it doesn't matter what happens in between all of these. What matters is the end as far as leading coefficient test goes. So if we have an even degree like x cubed, or excuse me, like x squared or x to the fourth, you could have x to the 100th, and this would apply. As long as that degree is even, doesn't matter what happens in the middle. If you have a positive coefficient, on the far left, it's going to go up, and on the far right, it's going to go up. If you have a negative coefficient, it's going to flip over. On the far left, it's going to drop, and on the far right, it's going to drop. Or if you have an odd degree, they're going to go in opposite directions. So if you have a positive coefficient, if you trace from right to left, so you're going to the left, it's going to drop off eventually. And if you're going to the right, it's going to rise eventually. A negative coefficient flips that over. It's going to rise on the left and fall on the right. Again, just practice. There's a lot of ways to make this make sense. I usually think of x squared and x cubed. But like I said, a lot of people, I've heard lots of fun different ways from students over the years, and there's no right answer to how to memorize this. So let's look at some examples. Let's describe the end behavior of these polynomials. So here we have f of x equals negative 5x to the fourth plus 3x cubed minus 7. All we care about for the end behavior for that leading coefficient test is that leading coefficient and that degree. So here they are in order. So x to the fourth is our highest degree, so our degree is 4. And our leading coefficient is negative 5. So we have an even degree, and we have a negative coefficient. So think for a second and think which way that's going to go. Remember, it's an even degree, so they're going to go in the same direction. And since we have that negative coefficient here, they're going to drop off on both sides. So it's going to fall to the left, and it's going to fall to the right. If you graphed it, you would verify that. Here we have f of x equals 3 plus 6x to the fifth minus 7x squared. Go ahead and pause this, give yourself a minute, and give it a try. When you're ready, you can see here that our highest degree is actually x to the fifth. So our leading coefficient is 6 and our degree is 5. We have an odd degree here, and we have an positive leading coefficient. So odd degree, positive coefficient. We know they're going to do the opposite. So they're going to the left is going to be the opposite way up to the right. Here, since it's positive, we know that it's going to fall to the left and it's going to rise to the right. Oh, there's the graph. I should have showed you that for that first one. So again, our leading coefficient here is 6. Our degree is 5. So it's going to fall to the left and it's going to rise to the right. And if we look at the graph, we see that. We move our pencil to the right, we're going to be falling. If we move our pencil to the right and graph it, we're going to be rising. Again, get some practice. These are fairly simple once it clicks. So a few more polynomial facts that can help us kind of complete the picture of what's going on. If we have a polynomial with a degree of n, then there can be only at most n x-intercepts. So it can only cross or touch that x-axis n times. So you think about x squared, right? That parabola can touch or cross the x-axis 0 times, 1 time, or 2 times. Okay, but it can't cross it more than 2. Additionally, it has at most n-1 turning points, so those local extrema. Again, think about a parabola. It only has 1 turning point. That's the most we can get with x squared, because 2 minus 1 is 1. So we can put all of this together and kind of compose a description of the function. So for each of the graphs that we're going to see, we're going to do a few examples, and hopefully you'll pause and play along and make sure that you're good to go, because you're going to see things like this on your test. You want to tell me the number of x-intercepts, the number of turning points, whether the leading coefficient is positive or negative based on that end behavior, whether the degree is positive, is even or odd based on that end behavior, and the minimum possible degree of the function. So let's do the first one together. Given this graph, let's count the number of x-intercepts. We have 1 and we have 2, so it crosses twice here. The number of turning points, it goes down, and somewhere around here it turns and goes back up, so we have 1 turning point. We see that it's going up in both directions, right? So we have to know, since it's doing the same thing on either side, that we have an even degree. And since it's going up on both sides, we know that that is a positive leading coefficient. And so putting all of this together, that we know that it's an even power, and then it crosses 2 times with 1 turning point, it has to have at least a degree of 2. So again, 2 intercepts right here, 1 turning point somewhere around here. We know that it's an even degree because the end behavior is the same in both directions. We know that it is a positive leading coefficient because it's going up in both directions. And that leads us to a minimum possible degree of 2. Okay, give this one a try. Pause, and when you're ready, you can move on. Okay, so x-intercepts. We see there's 1 here, there's 1 here, and there's 1 here. So there's 3. This one doesn't cross, it just touches and goes. Number of turning points, 1, 2, 3. I like to look at even or odd degree first. It's going down in both directions, so we know that's going to be an even degree. But since they're going down, we know that the leading coefficient is negative. And putting all of that together, we have 1, 2, 3 intercepts, but we also have 1, 2, 3 turning points. That means our minimum possible degree has to be 4. It can't be 3 for a couple of reasons. There's 3 turning points. So remember, turning points has to be n-1 at most. And also, remember, it's an even degree here. So our minimum possible degree here is going to be 4. Again, 3 intercepts, 3 turning points, even degrees, they're going in the same direction, negative leading coefficient because they're going down, not up, and our minimum possible degree is 4. Let's take a look at this one. Pause it if you'd like, and then we can discuss. So on this one, we only have 1 intercept right here. Okay. Number of turning points, we don't actually have any turning points here. It slows down, but it doesn't actually drop. We know that we have an odd degree because they're going in different directions. We're rising to the left and falling to the right. And since we know that our leading coefficient has to be negative because it's rising to the right and falling to the left, or rising to the left and falling to the right. So our minimum possible degree here is actually going to be 3. Now be careful here, because you might say, well, 1 would fit that. But sure, but 1 we know is linear. And this is not a straight line. So this could be a cubic, but it could not be just a plain x term. Do one more. Give it a try, and then we'll discuss. Number of x-intercepts, 1, 2, 3. Number of turning points, 1, 2. We know that our degree has to be odd because it's falling over here to the left, it's rising over here to the right. We know also that our leading coefficient must be positive because it's falling to the left and rising to the right. And our minimum possible degree is 3 here because we have those 2 humps and we have 3 intercepts. Here's just a nice summary from our text. It's prettier in the text. It kind of got distorted when I brought it into the PowerPoint. So you can get an idea of linears, possible shapes, quadratics, cubics, quartics. Tells you the degree by definition, the number of possible turning points, what happens to the end behavior depending on those leading coefficients, and what degree it is. Of course, x on its own is an odd degree. X squared is an even degree because of 2. X cubed is odd because of 3. And x to the 4th is even because 4 is even. So this table is very helpful to a lot of students also. So wrapping everything up, remember that even if you don't have access to a graph, you can say a lot about the polynomial based on its characteristics. But if you have a graph or you have a calculator, use it. It's a great way to check your answers. So as always, get some practice. Make sure that you do your homework. Use all the resources available to you. And if you need more help, remember you can reach out to me at any time. You can reach out to the Math Center. You have a lot of resources available to help us, help you. We are here to help you. My goodness, I cannot speak today. Thanks for tuning in, and I hope you'll join next time. Have a great day.